So today we got some design search autocomplete system. Autocomplete user may input a sequence with at least one word, and with special you are given a string array sentences and integer array times, both of length n, where sentence is I is previously typed sentence and times I is the number of times it was typed for each input character, except return top 3 historical hot sentences that have the same prefix as the part of the sentence already typed. Type the top 3, use ASCII order. If less than, return as many as you can. You need to read when the input is a special character, it means the sentence ends. Okay. Input. So this is first sentence. What the hell is that? Input char C. So this goes into autocomplete, and this is times it, and then I, nothing, A, this. Oh. Oh, okay, now I understand it. Okay, well, okay, interesting. So whenever we encounter this, we output empty array and we just add the sentence. Okay. Well, what do we want to do? Well, this screams try. So if we put the initial sentences into try, and then what we want, that have same prefix that we have already typed. And at each node we store how many sequences go through it. So when we are typing a sentence, we go down the tree, and if we can't, then whatever, nothing happens. We can actually even try to create the try. So what I'm thinking is that we add all sentences, and at each node we add the count of sequences that are going through there, and then when we are typing a word, we try to go down the try, right, and then count the number of sequences that go through there. Then we get that count and we increase it, and if that node doesn't exist, we return 0, but we need to return the sentences themselves. So essentially, how many times will input be run? At most 5,000 calls to input, so at most 2,501 characters are gonna be added. So tested sentence have a length of 200. Okay, so we have 100 sentences, so if we in each node of the try store the sequences, depends if we want to go for speed, because we need to retrieve the answers in that subtree. Okay, but it's try, so whatever. So let's make like a struct node, right? And now what does this node need to have? So which char it is, and And then what we need to have, like note, like child of alphabet size, I guess. Are they lowercase or space? Okay, we will make some. So const int k is 27 chars. So this is for our children, and we need to store also the indices of the sentences that can be finished from the node. And we also have to then store the sentences. So private sentences. Okay, that's fair. And then we also need trie. So we need a count, right? And let's do like character here. And then we need to have some insert method. Okay, let's do it here. So void insert node. And we want to do, okay, so we need some node, of course, to node root, and then we initialize root a new node, I guess that works. And then let's see if we are not gonna compile because of this, but that's okay. And nothing return here. Let's return this. Hopefully it's gonna type it. Okay, we are compiling, so let's do n is sentence size. Okay. And I++, and now we wanna insert into root sentences I times I, right? We are at 0 of index. I guess we want to insert sentence, we are at 0 of index. So then we have a const string sentence, okay, int index in that sentence, and then int count. Then we have some function which encode char character, which if char is space we return 26, else we return char minus lowercase a, classic. And now what we want to do, if index sentence size we return, we don't do anything. Okay, otherwise what we want to do is otherwise what? Otherwise we want to see, so char is sentence index, and now if char, if not node child int key is encode this char, and if child, if that's not true, then we want to do node child key new node, or let's do this node next, and then next character is char sentence index. Let's place this there. Next count, or let's call it count is count. Okay, and then we need to do indices, so next push back int const, const int sentence index. Okay, so we don't have to actually set this. We set it here, so we add this. Okay, and finally we do insert. No, what we need to do is wait, node child key is equal to next, and then this and this, and finally we want to do insert of node child key sentence index +1 count and sentence index. I think we should be compiling. Now we should be compiling. Okay, so maybe we have built a trie which has the answer. Okay, and now we need to store the string cur text or cur sentence. Great. So if c is equal to this, so we need to have some sort of current. We set current is equal to root cur is equal to root, and then we return. We also need to cur sentence is this. Okay. Okay, otherwise what we want to return is return so vector, actually no, okay, let's not do anything. So we try to, so try move, or let's call it like expand, right? So expand C. Let's do void for now, expand char C. So we have some current node, and if not current child, so int key is equal to this char keys encode char, and then if not child key, right, then we say we can't, so can't is true. Bool can't false, I guess, and then okay, that's fair. And then okay, so that's can't, and well, if you cannot move, then we return 0. So if can't, return this simply. Otherwise, can't return, right? Otherwise, we want to do current child key. Okay, so that's how we move. And then vector string ans for auto indices. Index in core indices and pushback sentences. Okay, and finally, if we are here, can't false, and we just do insert. We also need to do like core sentence plus equals C, and then what we want to do is insert. So insert into root current sentence with current index 0 one time. Oh, so sentences push back core sentence. Seems fair, I guess. I should order them based on their counts. Well, will they be unique, the edit sequences? Probably not. String count. Sound. Okay, so send occurrences. It's not good naming, but whatever. occurrences is in sentence index is high. What I'm doing right now is that sentences probably can occur multiple times. So what we are gonna do is, if sentence, what's it called, occurrences count sentences I, sentences index, then sentences index. Sentence index is sentences index of sentences I, else occurrences sentences I is equal to plus equals times I, and then sentences index sentences I is equal to I guess, or no, that's not updated, right? And then we push sentence index. Okay, so in fact we don't push it back. Sentence index is equal to sentences size if occurrences count if it was already there, then sentence index sentences index current sentence, let's see, current no, it's just cur, okay. Okay, else occurrences of plus equals, or just plus plus, whatever. Indices is equal to this, and then those are indices in that sort, indices begin, indices end, and then we do int index 1, well, let's call it I1 and I2, and return. And now what do we return? Well, we want to order them. If there are ties, what happens if there are ties? Use ASCII code order, smaller one appears first. Oh my god. Okay, so int O1 is equal to occurrences of sentences I1 and O2 occurrences of sentence is I2, and now if, or let's call it string sentence 1 is this, S2 sentence is I2, and now if O1 don't equals O2, so if they are same, so return O1 equals O2, we return S1 under S2, otherwise we return this. And then we sort the indices, min free indices size I++, ans push back indices I, return ans. What is this? Oh, it's already 50. Sentences index, occurrences index, un ore det. I can never type it. No. What the hell? How is that possible? But what do you mean? Here I initialized it as a pointer. It has to be separately declared, no viable conversion from, so on line 81. If it's already there, otherwise sentences push back current sentence index count as sentence index, so sentence index. This doesn't exist. Will you compile? Sentences pushback current sequence. Are you kidding me? What's current sentence? It's a string. Oh my god. Error non-void function. Let's see. Min free. Let's check this. And ans pushback. Okay, and now we are dead. Nice. After expand, we go to after expand, so dbg1, we go to dbg1, let's see if we get here, dbg2 probably not. Okay, so we don't get here. let's see, 1, 0, and sentence size is 0. Well, that's great, isn't it? Because if it's not there, then sentences push back okay, almost, we almost have it. Okay, so we got something. I love island, I love Leetcode, I love you. Why is I love Leetcode? When we type I, they are not ordered properly. Oh, because it should be like this. Okay. I hope there is no more output or no more debug. Let's see. Probably will crash, but wrong answer. Okay, ain't no way I'm debugging that. I really don't want to debug that, and I don't have time right now, so I'll get back to it later. So let's continue. My Firefox died, so okay. Question is, do I even use the node counts? Because I don't. That's weird. Well, I should draw the trie, but I don't have paper on me. Let's use this. So you are not gonna see anything, but just bear with me for a second. So first we have I, so just I first node, then we have space SR, so this is space SR, and then we have run Iron Man. From S we have island, quite a recent team, and then we have love you, so love space, and then we have you, and then we have the code. Okay, this is not even a tree, but whatever. So we are here, and now what happens? We have output, we type I, so that's the two most frequent ones. So I love you has frequency of 5, 5, 5. I love Leetcode has 2. Island has frequency of 3. and Iron Man 2. So this is 12. Okay. And then we do I. So we are at this prefix and we can pick all words. So we pick the three most frequent one, which is I love you, island, and I love Leetcode. Okay, that works. Then we go to space. Okay. And then we go to A, for which there is nothing, and then we also return nothing. So we add A with count 1. So this changes to 8 and this to 13. Right, so we are here and that's here. Then we go again I. Okay, same frequency, 5, 3, 2. Then we do space. So suddenly we have I love you, I love Leetcode, and IIA, right? And then we do another A. So that's IIA only, and then nothing. So we finish the sentence. So this should have an increase count of 2. This should have increased count of 9, and this should have increased count of 14. Okay. And then something breaks. Interesting. So we start with I, and we should have I love you, island, and then I space A, because so for some reason I love you is there. I'm not sure why, to be honest. So it breaks right here. So we expand the sentence with A. We got IIA. Maybe this. So I think something wrong with this. Okay, still nothing, but okay, so what we do? Okay, so well, we insert into root the current sentence from index 0, and what sentence index? What's that? Like this. IIA. sentences size. So first so it's in the last element. Fair enough. Oh. Okay. I love Leetcode has two. We put a greater or smaller one. Use ASCII code order. Sentences index of oh, wait a minute. So we just increase the... Okay, now I think the problem is the fact that because now, like let's say even here, if we have so it's not a new sentence, right? So did not occur twice, so we are only supposed to pretend that it all occurred once. Oh, whew. So we don't always push it back, so bool push sentence index, by default let's say true, and then if okay, and then push let's say false, and here we say to this, and then like this, and then we do the same thing here. So one, and then we do did not quite work out, I guess. Okay, if we are at I, then we are at space, and why is it returning I whatever? So let's see. Let's see. So we have input I, current character, I love you, I love Leetcode, IA. I'm starting to get lost in this. Let's see. Okay, let's see. Input C see. Sentences. There is nothing in the remote indices. Root encode I, maybe like this. I love you. So it really should only output this only one time. So I'm not sure how it came up with all this stuff. So let's move. X current okay. Oh. That's weird because I love you. I love Leetcode. That is weird, dude. I don't understand why it does that. Why is it duplicated there? So I only push back here. So I don't understand how this happened. So it's sentence, index, count, sentence, index, push sentence. Let's see. Okay. So why is it 0 and then suddenly it's 1 here? Where? Oh my god. Okay. Optional parameters. This is why Golang does not allow them, because you immediately fall into this shithole of debugging. Crazy. Please, bro. Okay, nice. Okay, probably could be made more efficient, like maybe we don't need the count. I remove that might help, and if something, I don't know. Let's see, from 268 to 269. Okay, now almost didn't help basically. Probably this is doable 10 times simpler, but I'm not sure I care. So simple try. Okay. We let's store the sentences in a trie, and each time we receive an input, we move down the trie if possible, and report all sentences corresponding to the sentences of the all sentences corresponding to leaves of the current subtree. Finally, when the user finishes a sentence, we insert it into the trie and note that we keep a count of we keep a counter with counter for each sentence. Order them. I'm not sure I want to describe the approach. I really am not sure. Time complexity. That's a tough one. So first we build it, which takes nm, and then each query we can answer in so amortized well, worst case all sentences are there, so so what do we do? Well, m is the length of the longest, so nm is the initialization. And then, well, what do? We move down the tree and then we insert it. That's amortized still om, but then we order it. So I guess so. Amortized. First we build a trie of the original n sequences of length at most m, which takes O and m. Then for each query we move in the trie along a single edge, and once the sentence of length at most m finishes, we insert into the trie. I mean, that could be combined, therefore inserting and moving down the tree is O of m operations every O of m input calls, meaning O1 amortized per call, but we also have to write out all sentences in a subtree for each sentence, of which there are at most n. So for all of the calls Oh, well, what's the worst case? Well, we write out all the sentences. If we store them in each, if we store the leaf sentences of subtree, or at least their indices to some sentence vector in some of leaf sentences, if we store the leaf sentences of each subtree in its root, we pre-processing query. For each query, remove a single and once the sentence of length at most and finishes, we insert into the trie. Therefore, inserting a nominator is OM operations every OM input calls, meaning on amount times per call. We also have to write out all sentences in a subtree for each in a subtree, of which there are at most n for each input sentence. If we store the leaf sentences, or at least there is some sentence vector of each subtree in their roots, we simply sort the sentences of a subtree corresponding to a node in which we finished descending. There is at most n of them, and they are of length at most m. Therefore, sorting them takes n m log n. But we do that once every m calls, giving us the final query time complexity O of n log n. This is the worst analysis of all time. Anyways, space is n time n, since at worst the sequences do not have since we have n sequences of length at most this is beta analysis, but who cares? I really don't want to write this. Goodbye.